All right, here we go with chapter 6, starting with 6.1. Please make sure you are keeping up with the homework because chapters 5 and 6 are some of the more challenging chapters in the book. So make sure that you are keeping up with the homework. Okay, so 6.1, take notes. Text me if you're having any questions here. Okay, so we are now starting with rational functions. So rational functions and simplifying. Simplifying rational expressions. Okay, so this will be done in 2 videos. All right, there we go. All right, so let's first talk about what a rational function is. So rational keyword ratio. So you should be thinking fraction, right? A ratio is a comparison between 2 quantities, like a fraction, A over B. Okay, so an expression of the form A over B, where A and B are polynomials. So these are more fancy fractions than what you're used to, like 2/3, right? Okay, so where A and B are polynomials, and very important here, B is not 0, okay? Because if it's 0, then it's undefined. Okay, here are some examples. There's an expression. There's another expression. Okay, so that's a rational function. Here's another one. 5m plus n, that's an expression. And m squared plus 4mn plus 4n squared. Okay, let me make this fraction bar a little longer. Okay, so that's another one. This is also one. Simple one. Okay. All right, so these are all rational functions here. Okay. And what we're going to be doing in this chapter is we're going to be looking at, just like with regular fractions, like if you have the fraction 2/4, you can simplify that to 1/2. We're going to be looking at how to do that with these guys here. How do we simplify them? And just like you learned how to add fractions, subtract fractions, multiply fractions, and divide them, same thing with these. We're going to learn how do we add them, how do we subtract them, multiply, divide them. Okay. Okay. So a rational function. This one we're going to be a little more brief with, and the focus of 6.1 will be on simplifying. Okay, so, but a rational function is a function whose equation is defined by a rational function. Well, not a function, a rational expression, is defined by a rational expression. Okay. So, for example, so up above, we just saw examples of rational expressions. So here, a rational function, well, first of all, we need our function notation, and it's defined by a rational expression, like 1 over x plus 8, okay? Or you could have g of t. And that would be defined by this rational expression, 5t squared plus t over t squared plus 6t minus 1. Okay, so these are examples of rational functions. So what we're going to do is, for this first video, we're going to look at rational functions. So we're going to be looking at domain again. So we're going to be looking at how to figure out what the domain is. And then we're going to look at, we're not going to look at how to graph these, but we're going to look at how to recognize the graph of these. Okay, so in being able to find these things called vertical asymptotes. Okay, so that's the first part. We'll focus on rational functions, and then in the second video, we'll look at simplifying rational expressions. Okay, so here, let's take a look at domain. Okay, so we've already looked at domain before. So let's take a look at this here. This is what you had before in terms of rational functions and the domain. You used to have something like this, find the domain, find the domain, and you had something like this, f of x equals 1 over x plus 8, right? And you said, oh, okay, well, it's going to be all real numbers except for -8, right? Because if x is -8, then we get 0 in the denominator, right? And if we get 0 in the denominator, it's undefined, okay? So here, the domain is everything. You can use everything, any number, except -8, right? Okay, so you would say your domain is all real numbers except 8. Okay. Different ways to say this. That's one way to say it. You can say all real numbers except this one. Those are my curly braces. Those are these symbols. Okay. So all real numbers except 8. That's one way to do it. And then there's also interval notation. So if you look at a number line, right, and here's 8, and you're saying, oh, it's everything except 8. Then when you write this in interval notation, you have to say, okay, way down here from -infinity all the way to here at 8, but not including 8. So we use parentheses, not bracket. And union. So we're basically saying this group over here together with this group over here. So 8, but not including 8. So again, parentheses, all the way to positive infinity. And that this here, interval notation is what will be expected from you guys. All right, so you only had the one value to exclude before. So now that you're familiar with factoring, you'll have something like this. Find the domain. And we'll be using this notation right here. Okay, the interval notation. Find the domain. And suppose that you have this now. 1 over x squared plus x minus 6. Okay, so now here, now you have to do a little bit more work. You have to actually factor it so that you can see what values you need to exclude. Okay, so over here, so you're basically trying to solve this quadratic. And we looked at how to solve quadratics in the previous section in the 5.9. Okay, so here, so here's the work. X squared plus x minus 6. We don't want that to be 0, so we're going to solve this. So we solve it by factoring. X times x. 1 positive, 1 negative, and 1 and 6 or 3 and 2. Looks like 3 and 2. Okay, so x plus 3, we don't want it to be 0, so x cannot equal negative 3. X minus 2 cannot be 0, so x cannot equal 2. So that's our domain. Our domain is all real numbers, but x can't be negative 3 and x can't be 2. Okay, so let's go ahead and graph that. So here's negative 3, open circle there. Here's 2, open circle there. So our domain is everything except those two numbers, right? Okay, so we have to describe each region here. Okay, so this region is negative infinity to negative 3, but not including negative 3, so put parentheses. This middle region is from negative 3 to 2, but not including them, so again, use parentheses. And then this third region over here is from 2 to infinity, but not including 2, so use parentheses. Okay, so this is what your domain would be. So that's how you express it. It would be nice if we could just say, oh, all real numbers except, right? All real numbers except negative 3 and 2. This is how you do it in interval notation. Okay, so you have to describe this set, negative infinity to negative 3, the middle set, negative 3 to 2, and this set, 2 to infinity. Okay. Okay, so that's what's going to be different here as far as finding the domain. Before, you only had this one factor down below. So there was just the one value that was excluded. But now you'll have to factor that and solve. Okay, and those are going to be the values you have to exclude. Okay. All right, let's go ahead and take a look at a few more examples. Find the domain. Okay, so let's take a look at this one here. Let's do f of x equals x plus 3 over x minus 4. Okay, so I put this one here because some students think that the domain is everything except negative 3 and positive 4. That's not the case. So remember, when you have a rational function, it's the denominator you're worried about. That's where the concern is. We don't want 0 in the denominator because then it makes it undefined. So that's where our restriction comes in. Over here, we don't care. We can have 0 in the numerator. That's fine. We can have anything in the numerator. But here, we cannot have 0. So over here, our domain is going to be all real numbers except for 4, right? Because if it's 4, then we get 0 in the denominator, which is undefined. Okay, so if you look at it in terms of a number line, here's positive 4. And it's everything except that. So we need to describe this set over here. So that's negative infinity all the way to 4, parentheses. And then we have to describe this set over here. So that's 4 to infinity, but don't include 4, so use parentheses again. Okay? So again, that's one of the old ones that you had before where you only have the one value to exclude. Okay, so let's take a look at some newer ones where you have to factor. So suppose that I have this here. Okay, so again, this has nothing to do with the domain right now, for now. Okay, so there are exceptions, okay, but in this section, you just have to worry about the denominator when you're looking for your domain. Okay, so here we have to factor, right? So x squared minus 9, we don't want that to be 0. So that's perfect squares. So that's x plus 3, x minus 3, right? We don't want that to be 0. So x plus 3, we don't want that to be 0. X minus 3, we don't want that to be 0. All right, so x cannot be negative 3, x cannot be positive 3, because if x is negative 3, then we get 0 in the denominator, which is undefined. If x is 3, then we get 0 in the denominator, which is undefined. Okay, so our domain is all real numbers except for negative 3 and 3. Okay, if we look at that in terms of a number line, here's negative 3, so we're going to exclude that. And there's 3, we're going to exclude that. But our domain can be any of these other numbers here, right? So these are 3 regions that we need to describe. Okay, so this first region is negative infinity to negative 3, but not including it, so I'll use parentheses. Union, this region here in the middle is from negative 3 to 3, but not including those numbers, so again, use parentheses. And this third region is 3 to positive infinity. Okay. All right. And let's take a look at one more. So here, suppose that you have h of x is equal to x minus 5 over x squared minus 3x plus 2. Okay. Again, this here, x minus 5, won't count, won't contribute to your domain. Okay, so we have to factor this, x squared minus 3x plus 2. We don't want it to be 0 because then it will be undefined. So let's go ahead and factor this, x times x. Same signs to make positive 2. They'll both be negative. There's only one way to make 2, and that makes negative 3x. All right, so x minus 2 cannot equal 0. X minus 1 cannot equal 0. So x cannot equal 2, and x cannot equal 1. So our domain can be any number except for 2 and 1. So let's take a look at what that looks like. Here's 1. We're going to exclude that number. Here's 2. We're going to exclude that number. So our domain can be any of these numbers, any of these numbers, any of these numbers. Okay? All right, so negative infinity to 1, parentheses, right? And then 1 all the way to 2, parentheses again. And then 2 all the way to positive infinity. Okay? So that's how you find domain. Now, as far as graphing, once you know which values to exclude, if you know how to do that, then you'll be able to recognize the graph. Okay, so let me do a quick example here. So for graphing, okay, so again, you only need to be able to recognize the graphs. Okay, so you actually won't be doing the graphs here. Okay, so look for values excluded from the domain. So that's going to be the main part, being able to find the domain, because if you can find the domain, then you should be able to find the graph. Okay, look for values excluded from the domain. So you will have vertical asymptotes. We'll talk about that in a second. Vertical asymptotes. are at these excluded values. Okay, so since x cannot equal those values, that means that you're not going to have your graph there. Okay, so you're going to have this sort of invisible vertical wall. Okay, and so that's kind of what the vertical asymptote is. It acts like a invisible vertical wall. Okay, so here, let's take a look. So suppose that I have this here, right? So our domain, I'm not going to use interval notation here because I just need to know which values are being excluded. Okay, so the excluded values, the only one is -8, right? So here, let me just write it out. Domain is all real numbers except for -8, right? So here at -8 is where you're going to have this sort of invisible vertical wall. Okay, so over here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so right here, this is at -8. You're going to have this invisible wall. Okay, and that's about as much as you'll need to figure out. And then what happens is you would end up with a graph like this and a branch there, and you would have a branch over here. Okay, but being able to recognize where that vertical asymptote is, that invisible wall, is going to be your key to being able to match the graphs. Okay, if you have another graph, another function that looks maybe something like this. Here, let's take a look at this one. Suppose that you have f of x is equal to 3x plus 2 over x squared plus x minus 6. Okay, so here, if I factor out the denominator, x squared plus x minus 6, right? Factor that out, xx plus minus 3 and 2. Okay, so x cannot be -3 and x cannot be 2. Okay, so then what happens is those are our excluded values over here. So here at -3, you would have this vertical asymptote. And also over here at 2, you would also have a vertical asymptote. Okay, so just be able to identify the vertical asymptotes. It's where those excluded values are. So if we look up here at these problems where we were looking for the domain, okay, so here, so at 4, you would have that vertical asymptote. Here, you would have it at -3 and 3. Here, you would have a vertical asymptote here at 1 and at 2. Okay, so long as you're able to figure out which values to exclude, then that's where you're going to have the vertical asymptotes. Okay, all right, so that is part 1. The next part, we will talk about how to simplify rational expressions.